An important aspect of coordination chemistry is the nomenclature of coordination compounds. The names and formulae of coordination compounds are written by employing the rules published by the International Union of Pure and Applied Chemistry, or IUPAC in short. Let's look at the rules framed by IUPAC for writing the formula of a complex. The first rule is the formula of the cation, whether it is simple or complex, is written first, followed by that of the anion. For example, in the complex shown here, the cation sodium is written first, followed by the anionic coordination entity. Similarly, in the complex containing a complex cation and a complex anion shown here, the complex cation AgNH32 is written first, followed by the complex anion AgCN2. The second rule is that within the coordination sphere, the symbol of the central atom is written first, followed by the symbols or formulas for the ligands in alphabetical order, irrespective of the charge on them. For example, in the complex shown here, the metal atom cobalt is written first, followed by the ligands ammonia and chloride. Polydentate ligands are also listed alphabetically. While listing in alphabetical order, the first letter of the abbreviation of the ligands is used to determine their position. For example, if a complex contains chloride and ethane 1,2-diamine, which is abbreviated as EN, then in alphabetical order, chloride is written first, followed by ethane 1,2-diamine. Another rule is that the formula for the entire coordination sphere is enclosed in square brackets. For example, in the complex shown here, the coordination sphere containing the metal atom copper with 4 bromine atoms are enclosed in square brackets. The cation potassium is written outside the coordination sphere. The formulae for polyatomic ligands and the abbreviations used for the ligands are enclosed in brackets. For example, EN, EDTA, PY, etc. are enclosed in brackets. For example, in the complex of cobalt shown here, the coordination entity contains the polyatomic ammonia ligand and the abbreviated ethane 1,2-diamine ligand enclosed in brackets. One more rule is within a coordination sphere, the metal atom as well as the ligands are listed without any space between them. For example, in the complex of cobalt shown here, the ligands ammonia, water and chloride are listed without any space between them. Yet another rule is that when the formula for a cationic or anionic coordination sphere is to be written without that of the counterion, then the charge with the number before the sign is written as a right superscript outside square brackets. For example, the complex ions of cobalt and chromium with the charge on the respective ions are shown here. Now let's see the IUPAC recommendations for writing the names of complexes. The first rule is, for coordination compounds that are ionic, that is, the coordination sphere serves either as the cation or the anion of the ionic substance, the cation is named first and separated by a space from the anion. For example, in the complex K4FeCN6, where the coordination sphere is an anion, the cation, potassium, is named first and separated by a space from the name of the anion. On the other hand, in a complex such as CONH3,6Cl3, where the coordination sphere is a cation, the cationic coordination sphere is named first, followed by the name of the counter anion, chloride. The second rule is, while naming the coordination sphere, ligands are named first, followed by the name of the central metal atom or ion with its oxidation state in Roman numerals in parentheses. Remember that irrespective of the charge on the ligands, they are named in alphabetical order. For example, in the complex PT-NH3-2Cl4, the ammonia ligands are named before the chloride ligands according to the alphabetical order, followed by the name of the metal ion with its oxidation number enclosed in brackets. IUPAC has also proposed certain rules for naming ligands. Anionic ligands are given names that end in the letter O. When the name of the free uncoordinated anion ends in ate, the name of the ligand is changed to end in ato, ATO. For example, the anion acetate is named acetato, sulfate as sulfato, thiocyanate as thiocyanato, and carbonate as carbonato. When the name of the free uncoordinated anion ends in ide, IDE, the ligand name is changed to end in ido, IDO. For example, the anion fluoride is named fluorido, chloride as chlorido, bromide as bromido, and iodide as iodido. Similarly, nitride is named nitrido, amide as amido, and azide as azido. Neutral ligands are given the same name as the uncoordinated molecule. For example, pyridine, dinitrogen, dioxygen, and triphenylphosphine. However, some neutral ligands are given special names. They are aqua for water, amine for ammonia, nitrosyl for nitric oxide, and carbonyl for carbon monoxide. Positive ligands, such as nitronium, hydrozinium, and nitrosodium, are named as such without any change. Another rule says, if several ligands of the same type are attached to the central metal atom, then their number is indicated by the prefixes di, tri, tetra, penta, etc. For example, in the complex CONH3, 3H2O Cl2, the 3-amine and 2-chlorido ligands are indicated by the prefixes tri and di, respectively. However, if the name of the ligand in question already includes a numerical prefix, then the prefixes like bis, tris, tetrakis, and pentakis are used. For example, the complex RuCl3PPH33 is named as tris-triphenylphosphine trichlorido ruthenium 3. Here's another rule. When the coordination entity is either neutral or cationic, the usual name of the metal is used. For example, the neutral complex shown here is named triamine trichlorido cobalt 3. Similarly, the cationic complex CrH2O 4Cl2Cl is named tetra aqua dichlorido chromium 3 chloride. Note that, in either case, the usual name of the metal is retained. However, when the coordination entity is an anion, the name of the metal ends with the suffix -ate. For example, the anionic complex NaPtNH3 3Cl3 is named as sodium triamine trichlorido platinate 2. For some metals such as iron, copper, silver, and gold, their Latin names ferrate, cuprate, argentate, and aurate are used. For example, the complex K2CuCl4 is named potassium tetrachlorido cuprate 2. Similarly, the complex NaAgCN2 is named sodium dicyanoargentate 1. Now is the time for practice. Apply IUPAC rules for writing the formulae in the first question and for writing the IUPAC names for the given complexes in the second question. Question 1. Write the formulae for these coordination compounds. Tetraamine aqua chlorido cobalt 3 chloride. Dichlorido bis ethane 1,2-diamine cobalt 3. Tetracarbonyl nickel 0. Question 2. Write the IUPAC names of these coordination compounds. Let's write the formula for the first complex. The coordination sphere is the cationic part in this complex. For writing the coordination entity, the symbol of the metal is written first, followed by the symbol or formula for the ligands. Hence, the coordination sphere is written as CO followed by NH3 and H2O ligands in brackets, followed by Cl. The next task is to balance the charge on the cation with the charge on the anion. Since amine and aqua ligands are neutral, and there is only one chloride ligand inside the coordination sphere, the charge on the complex ion is +2. Hence, two anions can neutralize the charge on the cation. Thus, the formula for the given compound is CONH3 4H2O ClCl2. Similarly, the formulae for the other two complexes are written as shown here. Coming to the second question. The first complex is a cationic complex and has 2 chloride ligands and 2 ethane 1,2-diamine ligands. The oxidation number of cobalt, as calculated here, is +3. Following the alphabetical order in naming the complex, chlorido-ligands are named first, followed by ethane 1,2-diamine. The number of chloride and ethane 1,2-diamine ligands is indicated by the prefixes di and bis respectively. Thus, the IUPAC name of the given complex is written as dichlorido bis ethane 1,2-diamine cobalt 3. Similarly, the IUPAC names of the other complexes are written as shown here. To explain the metal-to-ligand bonding in complex compounds. Different theories, such as the valence bond theory, crystal field theory, ligand field theory, and molecular orbital theory were proposed. Among these theories, the valence bond theory is the simplest, which satisfactorily explains the structure and magnetic properties of a large number of coordination compounds. The valence bond theory was proposed and developed by Linus Pauling. Here are some salient features of the theory. The central metal atom, or ion, has the required number of vacant orbitals for accommodating the electrons, donated by the ligands. The number of vacant orbitals is equal to the coordination number of the metal ion for a particular complex. The vacant orbitals of the metal atom or ion undergo suitable hybridization to yield a set of equivalent hybrid orbitals of definite geometry. The geometry of the complex can be predicted based on the coordination number and the hybridization of the metal atom or ion. As you can see from the table, when the coordination number is 4, the metal atom or ion may undergo either sp3 or dsp2 hybridization, and the complex may assume either tetrahedral or square planar geometry. When the coordination number is 5, the metal ion undergoes sp3 dehybridization and the complex has trigonal bipyramidal geometry. When the coordination number is 6, the metal ion may undergo either sp3d2 or d2sp3 hybridization. In either case, the complex has octahedral geometry. A ligand orbital containing a lone pair of electrons forms a coordinate covalent bond by overlapping with the hybrid orbitals of the metal ion. The magnetic moment of the complex can be used to determine its geometry. Note that the magnetic moment of coordination compounds can be measured by magnetic susceptibility experiments using a Gauy balance. The results of the experiments can be used to work out the shape of the complex. In the formation of a complex, if the metal utilizes its inner d orbitals, then such a complex is called an inner orbital complex or low spin or spin paired complex. On the other hand, if the metal utilizes its outer orbitals for complex formation, then such a complex is called an outer orbital complex or high spin or spin-free complex. Now let's apply these postulates to a dimagnetic complex, hexaamine cobalt 3 chloride. The cobalt atom in its ground state has the electronic configuration of argon 3d7 4s2. In the given complex, the cobalt is in +3 oxidation state. Thus, the cobalt +3 ion will have the configuration of 3d6 4s0. A glance at the configuration indicates that the complex is paramagnetic due to the presence of 4 unpaired electrons. Magnetic studies, on the other hand, have revealed that the given complex is dimagnetic in nature. This is possible only when the 4 unpaired electrons in the 3d orbital get paired up, contrary to the Hund's rule. As a result of electron pairing, 2 vacant 3d orbitals are made available for hybridization. Thus, 2 3d, 1 4s, and the 3 4p orbitals hybridize together to give a set of 6 equivalent d2sp3 hybrid orbitals. The 6 pairs of electrons donated by the 6 ammonia ligands occupy the 6 hybrid orbitals. You can see that there are no unpaired electrons left in the metal ion. Thus, the complex is dimagnetic and has octahedral geometry. As you can see, the metal ion has utilized its inner 3d orbitals for the formation of the complex. Hence, this complex can be called an inner orbital or low spin or spin paired complex. Similarly, in the case of complex ions such as hexaamine manganese 3 or hexacyanoferrate 2, pairing takes place contrary to Hund's rule, resulting in the formation of dimagnetic inner orbital complexes with d2sp3 hybridization. Now let us examine a paramagnetic complex, sodium hexafluorido cobaltate 3. In this complex also, cobalt is in +3 oxidation state. Magnetic studies indicate the paramagnetic nature of the complex. This is possible only when the outer 4s, 4p and 4d orbitals undergo hybridization. Thus, the cobalt ion undergoes sp3d2 hybridization and has octahedral geometry. As the outer d orbitals are utilized for hybridization, the complex is also called an outer orbital complex or high spin or spin-free complex. Similarly, in the complex ions, hexachlorido manganate 3 and hexafluorido ferrate 3, the outer 4s, 4p and 4d orbitals get involved in the hybridization to form outer orbital paramagnetic complexes with 4 and 5 unpaired electrons respectively. However, note that in the case of octahedral complexes formed by metal ions, such as titanium 3+, vanadium 3+, and chromium 3+, which have 1, 2, and 3 unpaired electrons, the magnetic behavior of these free metal ions and their coordination entities is similar. As you can see, in these ions, there are 2 vacant d orbitals available for octahedral hybridization with 4s and 4p orbitals. Thus, these octahedral complexes are always paramagnetic in nature. Now let's study complexes with the coordination number 4. You know that when the coordination number is 4, the complex may either have tetrahedral geometry or square planar geometry. We will first examine a paramagnetic tetrahedral complex, potassium tetrachlorido-nickelate 2. In this complex, nickel is in +2 oxidation state, and thus has the configuration of argon 3d8. The complex can be paramagnetic only if nickel undergoes sp3 hybridization and not dsp2 hybridization. Thus, the 4s and 4p orbitals hybridize together to give a set of 4 sp3 hybrid orbitals. The 4 electron pairs donated by the 4 ligands are accommodated in the hybrid orbitals. Hence, the given complex assumes tetrahedral geometry. Tetracarbonyl nickel 0 is an interesting example of dimagnetic tetrahedral complex. In this complex, the metal atom nickel is in 0 oxidation state. Experimental studies suggest this complex to be dimagnetic in nature. This is possible only when the paired electrons in the outer 4s orbital pair with the electrons in the 3d orbital. Thus, the metal atom undergoes sp3 hybridization to result in 4 sp3 hybrid orbitals. The 4 electron pairs donated by the 4 ligands are accommodated in these orbitals. Hence, the complex is a dimagnetic tetrahedral complex. Now, let us examine a dimagnetic square planar complex, tetracyanonickelate 2. In this complex, nickel is in +2 oxidation state and has the electronic configuration of argon 3d8. Magnetic studies suggest this to be a dimagnetic complex. This is possible only when the 2 unpaired electrons in the 3d orbital get paired up. Thus, the vacant 3d, 4s, and 2 of the 3 4p orbitals hybridize to form a set of 4 dsp2 hybrid orbitals. The 4 electron pairs donated by the 4 ligands are accommodated in these orbitals. The complex so formed has square planar geometry. Here is a question for you. What is the geometry of the complex if the spin-only magnetic moment of potassium tetrabromido manganate 2 is 5.9 Bohr magnetons? The coordination number of the Mn+2 ion in the given complex is 4. Hence, it may either undergo sp3 or dsp2 hybridization, and may have either tetrahedral or square planar geometry. However, the magnetic moment value of 5.9 Bohr magnetons clearly indicates the presence of 5 unpaired electrons in the complex. This is possible only when the metal ion undergoes sp3 hybridization. Thus, the given complex has tetrahedral geometry. Let us now look at the shortcomings of the valence bond theory. Although the valence bond theory successfully explains the formation, geometry and magnetic behavior of coordination compounds, it suffers from certain drawbacks. They are: coordination compounds are generally colored, but the valence bond theory does not explain the color exhibited by these compounds. This theory does not provide a quantitative interpretation of the stability of the complexes. It does not give the quantitative interpretation of magnetic data. It fails to predict the exact geometry of complexes with coordination number 4. For example, according to the valence bond theory, CuNH342+ has tetrahedral geometry. But X-ray analysis has proved that this complex has square planar geometry.